everybody! So today we are going to talk about 3 different questions, and we're going to start out with the basic question. So the basic question is asking, well, I'll just show you. It says, here are estimates of the daily intake of calcium in milligrams for 38 women between the ages of 18 and 24 years who participated in a study of women's bone health. So this is the data we are given. And it says, display the data using a histogram. Describe the distribution of calcium intakes for these women. So my part A is I created a histogram for the data. So I have the frequency on the y-axis and the calcium intake in milligrams on the x-axis. So, and we have to describe the distribution, not just graph it. So what I did is I used SOX. So the shape of this is definitely skewed to the right because of these 2 outliers, which is our second letter O. We have 2 potential outliers at 1,933 and 2,433. These 2 right here. And they're completely separated from the data, so you can tell that they are potential outliers. Our center is median is 845 and the mean is 926.0236, which I will show you how I got in part B. And our spread is, I got an IQR of 505 and a standard deviation of 429. So this is my histogram. So part B, down here, is asking to calculate the mean, the standard deviation, and the standard error. So the mean is the sum of all the data, obviously, divided by the total amount of women, which is 38. So I added all the data up, as you can see right here. I'll give you another quick glance at it, and divided it by 38, which is the amount of women. And I got 926.0236 milligrams. So that's our mean. Our standard deviation, I plugged into the calculator, I listed all the data and put that in list 1, and I went and found the standard deviation, which was 427.2295 milligrams. Now our standard error is our standard deviation over the square root of our total population, so which is 427.2295 divided by the square root of 38, which I got to be 69.306 milligrams. So part C is asking, find a 95% confidence interval for the mean. And when you see confidence interval, think pants. So P is the parameter, so the mean of daily intake of calcium for 38 women between the ages of 18 and 24 years old. For A, we should assume normality, assume independence, and the SRS is given. For N, the test we're going to use is the 1 sample T interval. And for T, this is what our equation is and all the work for it. So I have X bar plus or minus T star times S divided by the square root of N. So I have 926.0263 plus or minus the T star, which is 2.042, times standard deviation, which is 427.2295 divided by the square root of N, which is 38. And I got that to be just the T star times the standard deviation divided by the square root of N was 141.5224. And so that's plus or minus 926.03, which I got to be the lower interval was 784.5039, and the higher interval was 1067.5487. So our statement is we are 95% confident that the true mean of the daily calcium intake is between 784.5039 and 1,067.5487 for women ages 18 to 24. Now part D is asking, eliminate the 2 largest values and basically do pants all over again, find a confidence interval again. So as you could, or like remember from the first graph, these are the two outliers, so we are completely getting rid of those two, and which are, the values are 1,933 and 2,433. So we are going to scratch those, and we're going to do pants again. So the parameter is the same as it was before, we just eliminated the two outliers. A is the same, N is the same, so T. So since we got rid of the two highest ones, the mean is obviously going to change. So our new mean is 30,823 divided by 36, which is 856.1944. Our new standard deviation, after plugging that into the calculator, all the new data into the calculator, is 306.7296, and our standard error would be our standard deviation or the square root of n, and these change because our standard deviation changed from the two highest numbers being taken away, and also we have less data now since the two highest data were taken away. So our value of standard error is 51.1216. So we're still going to use the one sample t interval. So it's still the same equation. We're just going to have slight changes in numbers. So I have 856.1944 plus or minus the t star value of 2.042 times s over the square root of n, which is 306.7296 over the square root of 36. And I got 100, and these two numbers together equal 104.3903, and I'll move that up a little bit. And that will give us an interval of the lower one of 751.8040 and the higher interval of 960.5847. And over here, this is what we use to find the t-star value, degrees of freedom. Alright, so our statement is just a little bit different because of the interval. So I said we are 95% confident that the true mean of daily calcium intake is between 751.8040 and 960.5847 for women ages 18 to 24. So for the advanced question, the question is, you play two games against the same opponent. The probability that you win the first game is 0.4. If you win the first game, the probability you also win the second game is 0.2. If you lose the first game, the probability that you win the second game is 0.3. And it's asking, part A is asking, are the two games independent? So I said the two games are not independent. Part B, what's the probability that you lose both games? So what you want to do here is you want to take 0.6 and multiply that by 0.7, and you get 0.42. And that is a loss, so you have 42% chance that you will lose. Little frowny face. And part C is asking what's the probability that you win both games. So you take 0.4 and you multiply it by 0.2 and you get 0.08, which is a lot smaller. So you have an 8% chance of winning both games. So part D is asking, let random variable x be the number of games you win. Construct the probability model, which is this right here, for model X. So we have the X value, you have 0 wins, 1 win, and 2 wins. So right here we have to not win either of the games, so you lose, is 0.42 or 42%. To win one or the other, it's 50-50 chance, so 0.5. And to win both of the games, it's 8% or 0.08. So that is our probability model. And part E, is asking what are the expected value and the standard deviation. So the expected value would be, you can see it. So we go back up to our probability table, and it's this number times this number, and then you add this number times this number, and then add this number times this number. So you just basically do, so it's 0 times 0.42 plus 1 times 0.5 plus 2 times 0.08 equals 0.66. So that's our expected value. And our standard deviation is the square root of 0, or the x value, minus our expected value. So we basically just do that until all of the chart numbers are completed. So we have 0 minus 0.66 squared times 0.42. You get 0.42 there. And then you add that to 1 minus 0.66 squared times 0.5. You get that there. Plus 2 minus 0.66 squared times 0.08. You got that there. And that's all under the square root. And when I calculated that, I got the standard deviation equals 0.62. All right, on to our last question. Yay! All right, so the AP question is asking, investigators at the U.S. Department of Agriculture wish to compare methods of determining the level of E. coli bacteria contamination in beef. Two different methods, A and B, of determining the level of contamination were used on each of 10 randomly selected specimens of certain type of beef. The data obtained in millimicrobes / liter of ground beef for each of the methods are shown in the table below. So here's the table. And it's asking, is there a significant difference in the mean amount of E. coli bacteria detected by the two methods for this type of beef? Provide a statistical justification to support your answer, which means phantoms. Yay! So the parameter on the AP question, so basically what is the problem about, is the methods of determining E. coli contamination. The hypothesis is the HO is the mu of D equals 0, and the HA is the mu does not equal 0. So for A, I have assume SRS, which is given, assume independence, and assume normality, and we are using an alpha value of 0.05, and our degrees of freedom is 9, and then these numbers I calculated just for in the future when I have to plug them all in, so it's easier for me to see them. So the test that we're going to use for this equation is for this problem is a one sample match pairs t-test. So the equation for the one sample match pairs t-test is t equals x bar minus the mu over the standard deviation divided by the square root of n. So that is 0.29 minus 0 divided by 0.6297 divided by the square root of 10. So that is 1.4563, and when we go to our table, we get our p-value of 0.1792. So our O is just our p-value, again, which is 0.1792. We're making a statement, which is we are failing to reject the HO, and I will tell you why, and S. So we fail to reject the HO of a significant difference in the mean amount of E. coli bacteria detected by the two methods of this beef because the p-value of 0.1792 is greater than our alpha of 0.05.